This is SpaceTime Series 25, Episode 64. Coming up on SpaceTime, a strange neutron star discovered in a stellar graveyard. NASA to begin launching rockets into space from Arnhem this month. And the world's biggest rocket, Artemis 1, back on the launch pad at Cape Canaveral. All that and more coming up on SpaceTime.
Welcome to Space Time with Stuart Gary.
Astronomers have discovered a mysterious new type of neutron star. The star, which is catalogued as PSR J0901-4046, should be in a category for non-rotating dead neutron stars, assigned to a sort of hypothetical stellar graveyard. The trouble is, it's still rotating, very slowly, but the spin is still there, completing one rotation every 76 seconds and emitting an unusual radio signal. The discovery, reported in the journal Nature Astronomy, suggests the star could belong to a long-theorized class of ultra-long period magnetars, stars with extremely strong magnetic fields, and it even has characteristics associated with fast radio bursts, extremely powerful ultra-short flashes of energy, usually originating from distant galaxies. The study's lead author, Manisha Caleb, formerly from the University of Manchester and now at the University of Sydney, says the strange neutron star was detected from just a single pulse picked up by the Meerkat radio telescope in South Africa. Amazingly, Caleb and colleagues only detected radio emissions from the source for just 0.5% of its rotational period. But it was possible to confirm multiple pulses using simultaneous consecutive 8-second-long images of the sky in order to confirm its position. The authors say they were lucky that the pulsar beam intersected directly with the Earth. Because the majority of pulsar surveys don't search for periods this long, Caleb and colleagues have no idea just how many of these stars could be out there. It's therefore likely that there could be many more of these slowly spinning neutron stars in the galaxy, and that would have important implications for understanding how neutron stars are born, evolve, and age. Neutron stars are the crushed-down stellar cores of massive stars far larger than our Sun. Only about 3,000 neutron stars have so far been detected in our galaxy. That makes them fairly rare. When stars reach the end of their lives on the main sequence, having fused most of the hydrogen in their core into helium, the balancing act between gravity crushing a star down towards its center and nuclear energy pushing outwards ends, and gravity wins, causing the stellar core to collapse inwards under the star's own immense weight. Now, all this mass crushing down on the core causes a dramatic increase in pressure and temperature there. Eventually, conditions get extreme enough to trigger a helium flash, in other words, making it hot enough for the core to begin fusing helium into carbon and oxygen. At the same time, a shell of hydrogen outside the core has now reached sufficiently high pressures and temperatures to also begin burning. And this increased heat causes the star's outer layers to expand. And because these outer layers are now further away from the core, they also cool down. This combination of expansion and cooling transforms the star into what astronomers call a red giant. Eventually, stars like our Sun will fuse most of their core helium into carbon and oxygen, but they don't have enough mass to fuse carbon and oxygen into heavier elements, and so the fusion process ends. Their outer gaseous envelope detaches and floats away as a planetary nebula, leaving the stellar core exposed as a white dwarf, which will slowly cool over the eons. However, stars between 8 and 20 times more massive than the Sun face a very different fate. Because they're so massive, with high core temperatures and pressures, they fuse carbon into helium through a different process, and they then go on to fuse progressively heavier and heavier elements: carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, nickel, and eventually iron. But no matter how massive a star is, it's not massive enough to fuse iron into heavier elements. And so the balancing act between gravity crushing the star down towards its center and nuclear energy pushing outwards reaches a final conclusion, with gravity again being the winner, and causing the star to collapse in a spectacular explosion known as a core collapse supernova. Now, for stellar cores greater than about 1.44 times the mass of the Sun, figure known as the Chandrasekhar limit, this immense gravitational collapse is so great it breaks through what's known as electron degeneracy. That's the quantum mechanical effect arising from the Pauli exclusion principle, which prevents more than one fermion, such as an electron, from being in the same minimum energy level quantum state at the same time. Instead, it allows even further collapse, crushing the negatively charged electrons and positively charged protons together to form neutrons, hence the star's name. Although only a dozen or so kilometres wide, neutron stars are the densest objects in the known universe, other than black holes. In fact, just a sugar cube size of neutron star material would weigh 100 million tons. Neutron stars are thought to be composed of a solid, rigid outer crust or shell composed primarily of ions and electrons. Now, directly below this is theorized to be a fluid inner crust made up of electrons, neutrons, and atomic nuclei, a neutron-proton Fermi fluid and electron Fermi gas outer core, and an inner core possibly composed of quark-gluon plasma. At least that's the theory. Caleb says the newly discovered neutron star seems to have at least 7 different pulse types, some of which occur at regular intervals. It's the beginning of a new class of neutron star. She says how or whether it relates to other classes is yet to be explored.
So, neutron star is an extremely dense remnant that's left over after a massive star undergoes a supernova explosion. The neutron stars are typically about 20 kilometers across, and a teaspoon of neutron star material would weigh about 4 billion tons on Earth.
And what you guys have found using Meerkat in South Africa appears to be a neutron star. It's rotating. Neutron stars often rotate. They rotate because the conservation of angular momentum. As they contract, they rotate faster and faster because they start out, as you said, as regular stars. But eventually they get old and that rotational rate slows down. And this is where your discovery comes in. It's showing a number of things, isn't it?
That's right. So the thing of what makes our star unique is that it rotates extremely slowly. So it completes one rotation every 76 seconds. And basically, when neutron stars are born, they have very short rotation periods. And as they age, because they dissipate energy, they slow down and they attain longer periods. But the thing is, when they attain longer periods, you don't expect them to emit in the radio anymore. And our neutron star resides in what we call the neutron star graveyard. So it has past what we astronomers call the death line, and it's in the graveyard where we don't expect any emission at all. But we do see emission. So this is quite interesting because we either don't understand the neutron star graveyard or we don't understand how neutron stars evolve.
When you say rotate very fast, we're talking about millisecond speeds, aren't we? We're talking about many times a second in some cases.
Absolutely, yes. So the shortest known neutron star rotates with a spin period of about 1.4 milliseconds. And until our discovery came along, the longest spin period was 23.5 seconds. So ours is considerably longer than the slowest known neutron star until ours came along.
What's the hypothesis? What do you think is causing this star to still give out bursts in the radio at such a slow rotational rate?
So that's the thing we don't quite know, and it's something for the theorists to explore. But what is extremely interesting about our source is that it exhibits 7 different types of pulses. So there are 7 different varieties of shapes of the single pulses that the source emits. And that's quite diverse given what we've seen in the other 3,000 known neutron stars in our own galaxy. And there's one particular type of pulse which is quasi-periodic in nature. So it basically means there are several short duration pulses closely packed. And we speculate that this could be caused by seismic vibrations or starquakes on the surface of the neutron star, which could be providing us with very valuable insight into the actual extreme physics that's producing the emission. But we don't really know what this emission is just yet.
There's a lot about neutron stars we don't understand. We're not sure about what's happening deep inside them. Are they quark stars deep inside? Who knows? You're finding some interesting clues, it could be a magnetar or even a fast radio burst. That's really interesting, isn't it?
Absolutely. So even though this is the spin period and what we call the period derivative, which is the rate at which the neutron star is slowing down, is characteristic of pulsars, the single pulse shapes is very reminiscent of magnetars, and also the magnetic field that is associated with the source is extremely high, which again is characteristic of magnetars. So we're still not sure, the jury is still out on whether this is a high magnetic field pulsar or a magnetar, and we're going to need more observations at different wavelengths to understand which category this belongs to, or whether it is in a category of on its own. But the quasi-periodic pulses are particularly interesting because we've seen some fast radio bursts exhibit similar pulses, but whether our source exhibits the same sort of energies that fast radio bursts emit is something that we haven't seen yet. So continued monitoring of the source will tell us whether it is indeed capable of producing the same sort of large amounts of energy that is typically seen in a fast radio burst pulse.
We're now seeing this emergence of neutron stars with magnetars and fast radio bursts. That's sort of the way other observations are going too, especially with fast radio bursts and what they're likely to be, because right now they're still a mystery. But the more we find out about them, especially with fast radio bursts that are repeating, we're finding out that they seem to hang around in the same sort of neighborhoods as where you'd expect characteristics for magnetars to be. And now we're seeing another example here of something which sort of fits into the broad group.
Because most theories for what fast radio bursts could be based on our observational characteristics tend to be, like most theories which can quite elegantly account for all that we observe, are magnetars. And the fact that we see FRB-like pulses from this particular source, at least in terms of the pulse shapes, suggests that this could maybe produce FRBs in the future. And it also suggests that maybe there is some sort of an evolutionary link between magnetars and fast radio bursts, which occur well outside our galaxy. I guess we're going to have to observe this source more to figure out whether there is indeed a link.
That's got to be exciting.
That is indeed very exciting.
So where to next? You talked about looking at other areas of the electromagnetic spectrum, and also I guess you're looking for more?
Yes, I think this is just the beginning, because right now this particular neutron star is off in a little class of its own, and there are potentially hundreds more of these sources just waiting to be discovered. I think upcoming and future plans to search for more such objects will really help us understand the galactic neutron star population a bit better, and also potential links to fast radio bursts or even other types of neutron stars.
Until now, you did know this was there, so you didn't know what to look for. Now you know it's there. You're going to be looking for more of them.
Exactly. I think that's what astronomy is all about. You're exploring or finding the unknown unknowns. A lot of these discoveries are serendipitous, and then you discover that there indeed are more out there. You just need to look for them.
Meerkat's been wonderful for this sort of thing, hasn't it?
Absolutely. Meerkat is the precursor to the square kilometer array, which is going to be the future of radio astronomy. And the fact that we're finding such exciting objects with Meerkat just shows what the future SKA is capable of.
That's Manisha Caleb from the University of Sydney. And this is SpaceTime. Still to come. NASA to begin launching rockets from Arnhem Land this month. And the world's biggest rocket, Artemis 1, back on the launch pad at Cape Canaveral. All that and more still to come on SpaceTime. NASA's listed June the 26th as the preferred launch window for the first of 3 sounding rocket flights to be conducted from Equatorial Launch Australia's new Arnhem Space Centre in the Northern Territory's Gove Peninsula near Nhulunbuy. The flights will be the first for NASA from a commercial launch facility outside the United States, and will be the first time the American agency has launched rockets in Australia since 1995. Back then, launches were conducted from the Australian Air Force's Woomera Rocket Range. As part of the current program, 2 more suborbital missions will launch from Arnhem on windows opening on July the 4th and July 12th. Now, 2 of the flights in this campaign will focus on studying Alpha Centauri A and B, the 2 primary stars in the 3-star Alpha Centauri system. Alpha Centauri is the nearest star system to the Sun and can be best seen from the southern hemisphere. In fact, if you look at the Southern Cross, Alpha Centauri is the more distant of the 2 pointer stars. The 3rd launch will focus on studying X-rays emitting from the interstellar medium, the space between the stars. The 3 flights will each be launched aboard a 12.2-metre tall Canadian 2-stage Black Brant 9 sounding rocket flying a suborbital apogee of 300 kilometres. The Black Brant's no stranger to Australia, having first flown from the Woomera Rocket Range back on November the 9th, 1976. That was part of a joint Australian and Canadian program to study the Earth's ionosphere. Later, NASA also launched a number of Black Brants from Woomera. Back in September 2021, around 20 NASA personnel from the Wallops Island Flight Facility on the Virginia Mid-Atlantic coast travelled to Arnhem Land to set up equipment for the current campaign. Another 60 NASA staff arrived last month, with a further 15 science team members flying in this month. Nikki Fox, director of NASA's Heliophysics Division in Washington, D.C., says the flights will allow scientists to explore how a star's light can influence a planet's habitability. The first launch, targeted for June the 26th, will carry an X-ray quantum calorimeter developed by the University of Wisconsin-Madison. It uses unique X-ray detectors, cooled to just 1/20th of a degree above absolute zero, and used to measure interstellar X-rays with unprecedented precision to better understand the interstellar medium and its influence on the structure and evolution of galaxies and stars. The second mission, that's the one slated for the 4th of July, will carry a suborbital imaging spectrograph for transition region irradiance from nearby exoplanet host stars, in this case Alpha Centauri A and B. Developed by the University of Colorado Boulder, it'll study the ultraviolet light from these stars and how it affects the atmospheres of planets around them, including the gases thought to be signs of life. The third mission, targeted for launch on July the 12th, will carry JUICE, the Dual-Channel Extreme Ultraviolet Continuum Experiment, also from the University of Boulder, Colorado. JUICE will measure a so far understudied part of the extreme ultraviolet spectrum. These measurements will help astronomers model stars similar and smaller than the Sun, as well as better understand their effects on planetary atmospheres. Located just 12 degrees south of the equator on the Gulf of Carpentaria, the Arnhem Space Centre is ideally suited for equatorial missions, and its management hopes to ramp up operations over the next 5 years. Equatorial Launch Australia is already in advanced commercial discussions with 9 other major rocket companies. They hope to carry out at least 2 additional launches before the end of this year, eventually ramping up to more than 50 launches a year by 2025. As well as Equatorial Launch, work's proceeding on 3 other commercial space launch facilities. Southern Launch are developing a polar launch facility at Whalers Way on the Eyre Peninsula near Port Lincoln. It would provide orbital launches over the Great Southern Ocean, while a second Southern Launch facility near Nhulunbuy, 40 kilometres from Ceduna on the South Australian west coast, would track over the Nhulunbuy, allowing test rockets to be fired with the jettison stages and payloads then collected. Meanwhile, construction's now underway on the Bowen spaceport at Abbott Point in North Queensland, and it'll be used for orbital launches by Gilmour Space Technologies' new Ares rocket. This is SpaceTime. Still to come, the world's biggest rocket, NASA's SLS Artemis 1, is back on the launch pad at Cape Canaveral. And later in the science report, the world's first exascale supercomputer and the world's largest and oldest plant. All that and more still to come on SpaceTime. NASA's SLS Artemis 1 moon rocket's back on the launch pad in Florida after a series of modifications in preparation for another attempt at a pre-launch wet dress rehearsal. It took about 10 hours for the massive 98-metre tall rocket to travel the 6.8 kilometres from the Vehicle Assembly Building at the Kennedy Space Centre to the neighbouring Space Launch Complex 39B at the Cape Canaveral Space Force Base aboard its crawler transporter. A new attempt at the wet dress rehearsal is now slated for June 19th. These tests are designed to demonstrate that the SLS can be safely loaded with propellant and oxidizer, carry out a series of launch aborts, and still lift off safely. Previous wet dress rehearsals back in April were aborted following a series of issues with ground equipment on the launch pad, including valve, fueling, and leak issues. Engineers addressed the liquid hydrogen system leak in the tail service mast umbilical on the mobile launch pad, which was connected to the interim cryogenic propulsion stage. It seems it's common for no leaks to show up at normal air temperatures, but then develop once cryogenic temperatures are established. The solution is simply tightening the umbilicals at regular intervals. Technicians also replaced an interim cryogenic propulsion stage gaseous helium system check valve and support hardware, modifying the umbilical purge boots responsible for the quick disconnect of the mobile launch pad arms from the SLS during liftoff. They found a small piece of rubber was preventing the valve from sealing properly. Now, there's nothing wrong with the valve itself, but mission managers wanted to know where the bit of rubber came from. They also checked the Orion spacecraft itself just to make sure it was okay following exposure to the thunderstorms and heavy rain which deluged the Cape Canaveral Launch Complex during the April test. While they were at it, they also updated software on the spacecraft in order to address issues encountered during core stage cryogenic tanking of both the liquid hydrogen and liquid oxygen during the April test. And contractors looking after the gaseous nitrogen system at the launch complex have also completed a series of upgrades. Now, there was nothing broken on the nitrogen system, which is used to purge the rocket, including its umbilical plates. But the 2,608-ton SLS is so big, it needs far more gas nitrogen, and the existing system was finding it difficult to meet the demand. So, extra capacity was added. Engineers have also undertaken some of the forward work originally slated to take place in the Vehicle Assembly Building after the wet dress rehearsal was complete. This includes installing hardware elements for the Callisto technology demonstration, a flight kit locker, and assemblies for a space biology experiment. The upcoming wet dress rehearsal should take about 48 hours. It includes a full countdown simulation, which will see the rocket initiate all pre-flight systems and cycle right through all fueling procedures right up to the moment just before engine ignition. The test also includes a series of holds and several launch aborts. They're designed to test systems and stress components under several different simulated weather scenarios and launch conditions. The rehearsal will run the Artemis 1 launch team through operations to load propellant into the rocket's tanks, conduct a full launch countdown, demonstrate the ability to recycle the countdown clock, and also drain the tanks to give them an opportunity to practice the timelines and procedures that they'll have to use during launch. The launch team will start by activating the facilities needed to launch and formally begin the countdown sequence. Teams at the Launch Control Center at Kennedy will connect with staff at Mission Control at NASA's Johnson Space Center in Houston, Texas, the Space Force Eastern Range Administration, and the SLS Engineering Support Center at the agency's Marshall Space Flight Center in Huntsville, Alabama. Launch controllers will power on different rocket and spacecraft systems along with ground support equipment. They'll then load more than 2,650 tons of cryogenic propellants, including both liquid hydrogen and liquid oxygen, into the SLS core and upper stages at the launch pad, while the rocket's on the mobile launcher, following a detailed timeline identical to the one they'll actually use on launch day. They'll practice every phase of the countdown, including weather briefings, pre-planned holds in the countdown, conditioning and replenishing of propellants as needed, and validation checks. During the wet dress rehearsal, once launch controllers reach the point just before the rocket's RS-25 engines ignite on the launch pad, they'll stop and recycle back to the T-minus 10-minute point, and then resume the countdown once more after a hold. Mission managers will then deliberately halt the countdown about 10 minutes before simulated liftoff in order to demonstrate stopping at launch and draining the propellants from the rocket. Launch controllers may decide not to proceed with a launch if a technical or weather issue arises during or prior to a countdown, so demonstrating the ability to remove propellants will ensure teams are prepared for various launch day scenarios. Several days after the wet dress rehearsal, Artemis 1 will be rolled back into the vehicle assembly building. There, technicians will remove a series of sensors specifically used for monitoring during the wet dress rehearsal. They'll then charge Orion and other system batteries, stow late-load cargo into Orion, and run final checkouts on several systems. NASA then will review data from the rehearsals before setting a specific target launch date for the Artemis 1 mission. Orion and the SLS will then roll back out onto the launch pad for the final time. Now, if all goes well during this window launch period, Artemis 1 should fly during a launch window opening on August the 10th, in the process becoming the most powerful object ever to lift off the Earth's surface and producing some 8.8 million pounds of thrust. Its 25-day maiden voyage will be an unmanned test flight taking it some 65,000 kilometers beyond the Moon in retrograde orbit. The mission will carry several experimental payloads aboard the Orion capsule and will deploy 13 6-unit CubeSats along the way before returning to Earth and splashing down in the North Pacific Ocean. Now, if the mission goes according to plan, Artemis 2 will follow in 2024. That'll carry the first manned Orion crew capsule on a 10-day mission around the Moon and back. This would be followed in 2025 by Artemis 3, which would return humans to the lunar surface on what's expected to be a 30-day mission. This is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday, and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.